what's the size of this one? Well, it's this group, and what's the order of this group? Well, it's n, right? Here it is. Here, this group consists of elements, residue classes. The residue class 0, dot, 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 the residue class n minus 1. So this contains n elements, right? And this one as well. It consists of powers of the generator, little a, and little r, the actual power, ranges from 0 to n minus 1. Also n total. So these two groups, these two classes, have the same size. As groups, they have the same order. Okay, now we have a theorem. Theorem 27 on page 76 of your text, if you're using the text. Okay. So if you can remember what that theorem says, if the two sets are of equal size, and you have a mapping that is a surjection, therefore it's an injection. And if the two are the same size, then if that mapping is an injection, therefore it's a surjection. So if it's one, it's both. So if it's either an injection or a surjection, therefore it's a bijection. Okay? So since we've already proved that it's a surjection, therefore it's an injection. So we don't have to do the work, we just use the previous result. Now that's a... Well, you know that, right? I mean, once you've got previous results, you've proved them, you know they're true, well, then, if the opportunity arises to use them, then do. Okay? Okay, so we've now proved that this F, the mapping, is bijective. Okay? Now that leaves the F of m n thing. Now this form, we have to prove that. Now that's a general form. Let's translate it into our problem. So what's the binary? Now the binary operator is plus. Okay, so let's translate this. So show. This is what we have to show. Show. Now m. We uses R and S. Well, instead of M and N, he's using R and S in the text. Okay, so R, binary operators, that'll be plus S. Okay. So show that equals this right hand side. This is what we have to prove. So that will be of the form now the binary operator, well, it's just plus, okay? F of S. That's what we have to show. So let's work on this side, the left-hand side, and try to prove this. Okay, so let's work on this. So this is now, I've rubbed it off, but from residue class theory, remember, you just add these two inside. So this is you just add these two inside. Okay. Now have a look at this. So we can translate that. We can translate this into this. Right? Now instead of having R, we've got R plus S. So we'll have an R plus S here. So this is equal to A to R plus S. Okay? But this, you can split this up, so that's just A to the R, A to the S. Right? But what is A to the R? Well, what's this? Right? So it's F R N F S mod n. Right? how do I need the binary? I got a plus. Oh, it's a power. Yeah, okay. Yeah, in this case, the binary operator here is multiplies, right? Because you have two powers. Okay, so it's just times, right? So just multiplication. So that's correct, all right? So we've proven the third part, where you have to, this FMN thing. So we've done that. So that's that. Now, so let's discuss a little. So any cyclic group that's order n is isomorphic to this. Okay. So in effect, any cyclic group of order n is isomorphic to any other. Like, how can I put that? Say you have three groups, and A is isomorphic to B, but C is also isomorphic to B. Therefore, A and C are isomorphic to each other. Right? Makes sense? I mean, because they all have the identical group table, so they're all isomorphic. They're the same group from the point of view of a group theorist. So all cyclic groups of this order n, they're all isomorphic to this one. If they're all isomorphic to this one, therefore all these groups, cyclic groups, are, and here's the punchline, they are all isomorphic to each other. Okay? So, in other words, any cyclic group of order n, they're all isomorphic. They're all the same group. So you, in effect, you can talk about the, as in the sense the only one, you can talk about the cyclic group of order n. From the group theorist's point of view, there's only one, right? Because all the what you think are different, if they're cyclic and of order n, the order of the group, cyclic group is n, then all of them are isomorphic. So they're the same group. So there's only one of them. There's only one group that's cyclic in order n. So you can talk about the cyclic group. Okay? Alright? Again, I need to clean the board. I think I'll do the next part tomorrow. But I'll give you a bit of a lead in. It's a bit of a change of topic, somewhat. So far in this lecture, we've pretty well been talking about how to prove that two groups are isomorphic. And all the the various steps you go through, well-formed and bijective, and the FM thing. This. But what about when it's the other way around? What if you are given two groups and you're suspicious that they are in fact not isomorphic? How do you prove that? Well, I guess the very first test, very simple common sense type test, is to look at the two groups and ask the question, what are their orders? The orders, the size of the two groups. If the order of group 1, the order of group 2 that you're comparing, if they're different, if those two orders are different, the sizes have different numbers of elements, then there's no way you can get a one-to-one mapping between them. Right? You can't map bijectively. You can't map one-to-one when there's more in one than the other. So immediately you can throw out the idea that they might be isomorphic. So the very first test you would do when you have two candidate groups and you're trying to see whether they are not isomorphic is just to test their two orders, and if they're different, then immediately you know they are not isomorphic. Okay, but it happens that they may have the same order, the same number of elements, but still not be isomorphic. So how do you go about testing that? And there's lots of techniques. So the next section that I'll talk about will be giving you one method one trick, if you like, that allows you, it helps you distinguish, to see whether two groups are not isomorphic. It involves a proof, but I'll do that next time.